One of my biggest fears as a software engineer is that a feature I deploy to production on a Friday breaks over the weekend, and I'm then forced to wake up in the middle of the night to deal with dozens of unhappy customers. Yes, we are lucky enough that the worst thing that could happen if we mess up at our job is to get yelled at by a stranger. But imagine that the product you are working on is Cloudflare, which sits between users and around 20% of all websites on the internet. To get a sense of the scale, last year Cloudflare handled an average of more than 81 million HTTP requests every second, reaching more than 129 million requests per second during peak traffic. That's probably a bit more than the Java 7 enterprise application you are maintaining at work. So when Cloudflare breaks, all our favorite apps go down with it. Towards the end of 2025, the company suffered 2 major global outages less than 3 weeks apart, and both incidents were caused by relatively small configuration changes that propagated across its infrastructure within seconds. So, in this episode of The Blueprint, we'll look at how Cloudflare accidentally took down parts of the internet, why configuration files can be just as dangerous as software deployments, and how concepts like Canary releases, Graceful degradation, and blast radius isolation can stop one bad change from becoming a global incident. Or, in other words, we'll figure out how the hell a relatively small company is keeping the internet running. At its core, Cloudflare offers a very simple service. When you visit a website, it can act as a reverse proxy. Cloudflare receives the request on behalf of the website, checks it for attacks, potentially serves the content from a nearby cache, applies firewall and routing rules, and only contacts the original server when necessary. This improves performance and protects the origin server because users, bots, and attackers are no longer connecting to the end server directly. So Cloudflare clients get a very simple solution to a very hard problem. In order to provide these services, Cloudflare operates hundreds of data centers around the world, and many of them point to the same IP addresses using a routing technique called Anycast. Normally, an IP address points toward one specific location, but with Anycast, the same address is announced from many locations at the same time, and the internet routing protocols direct your request toward a nearby Cloudflare data center based on the current network conditions. And since the internet's routing system does most of the work, Cloudflare does not need to manually assign every user to a region. On top of that, if one location becomes unavailable, traffic can often be redirected somewhere else. But, besides distributing traffic, Cloudflare also needs to distribute enormous amounts of configuration. Every time a customer changes a DNS record, creates a firewall rule, modifies a redirect, or updates a security setting, that change needs to reach machines all around the world as fast as possible. Cloudflare does this using an internal distributed key value system called Quicksilver, which can propagate configuration changes across the world in seconds. The problem is that the ability to distribute something globally within seconds is also the ability to break something globally within seconds. To solve this, Cloudflare had developed careful deployment systems, so when engineers release new changes, they would be deployed gradually. The release might first receive internal employee traffic, then move to a small number of data centers, then reach a limited percentage of customers, and eventually expand to the entire network. At every stage, the deployment system closely monitors metrics such as error rates, latency, and resource usage, and if the new version behaved badly, the rollout could be stopped or automatically reversed. This deployment architecture is called Canary deployment. And this is your awesome trivia of the day. The term comes from the canaries miners once carried underground. Since the birds were more sensitive to toxic gases, they would react before the miners were seriously affected. In software, the canary is a small amount of real production traffic. If the canary starts producing errors, you stop the deployment before every server joins it. Cloudflare applied this model to software releases, but many configuration changes were still deployed everywhere almost immediately. And this caused a huge issue in November 2025. The incident began inside its bot management system, which analyzes incoming traffic and assigns requests a bot score. A low score means the request probably comes from automation, while a higher score suggests that it is more likely to be a real person. To calculate this value, Cloudflare uses machine learning models that examine a collection of features. These features might include characteristics of the HTTP request, browser behavior, network information, and patterns associated with automated traffic. The runtime receives a configuration file describing the features expected by the current model, and that file is regenerated regularly from a ClickHouse database and distributed across Cloudflare's network. Under normal conditions, the model used around 60 features, and the proxy supported a maximum of 200. But because of a permission change, users could fetch data from multiple databases. The query generating the bot configuration filtered results by the table name, but it did not also filter by the database name. So after the permission change, the same query started returning duplicated rows from two separate data sources. As a result, the generated feature file became more than twice as large, exceeding the limit supported by the proxy. So Cloudflare's network started failing, systems were producing errors, then returning to normal, only to start failing again without an obvious deployment taking place. The reason was that the file was regenerated every 5 minutes, while the ClickHouse permission change was gradually reaching the database cluster. If the query landed on an updated node, it produced the oversized file. If it landed on an older node, it produced a valid one. Quicksilver then did its job perfectly and distributed whichever version it received across the network. Eventually, every ClickHouse node received the permission change, every generated file became invalid, and the entire system settled into a much easier state to debug because the entire system was completely down. When the oversized file reached Cloudflare's Rust-based proxy, it exceeded the hard limit of 200 features. The validation code returned an error, but instead of handling it gracefully, the application called unwrap on the Rust result. Of course, even at Cloudflare's scale, developers don't waste their precious time on trivial things like handling exceptions. We all love the happy path. So the process panicked and started returning HTTP 500 errors. But the real problem was that Cloudflare treated internally generated configuration as trusted input. When the data comes from another internal service, developers often assume that it must be correct. In a distributed system, however, internal data is still external input from the perspective of the service receiving it. Cloudflare should have rejected the new file and continued using the previous working version. Instead, the invalid configuration replaced the valid one and crashed the proxy. So a duplicated database result became a broken machine learning configuration, which crashed the proxy, which then affected the tools used to respond to the outage. This is what we generally call a cascading failure. One component breaks, but because other services depend on it, the problem spreads through the system and starts producing failures that appear completely unrelated to the original cause. This was Cloudflare's worst outage since 2019. And then, less than 3 weeks later, they managed to create another one. On December 5th, Cloudflare was responding to a critical vulnerability affecting React server components. Its web application firewall inspects request bodies for malicious payloads. So the company began increasing its inspection buffer from 128 kilobytes to 1 megabyte. This first change was deployed gradually, using the safe deployment system we discussed earlier. During the rollout, however, engineers discovered that an internal WAF testing tool did not support a larger buffer. Since the tool was not needed to process customer traffic, they decided to disable it. Unfortunately, this second change was deployed using the global configuration system, so it reached the entire system within seconds and, surprisingly enough, on Cloudflare's older proxy implementation, disabling the tool exposed a Lua bug. The code attempted to access an execute field on an object that did not exist, causing the proxy to return HTTP 500 errors. The incident lasted around 25 minutes and affected applications representing approximately 28% of Cloudflare's traffic. The technical causes of the two outages were completely different. The first involved ClickHouse, machine learning features, and Rust. The second involved a firewall tool, a configuration flag, and Lua. But architecturally, they were the same incident. A configuration change reached the entire network almost immediately, the receiving software encountered an unexpected state, and there was no graceful fallback. After the second outage, Cloudflare launched an engineering program called Code Orange Fail Small. They cannot guarantee that engineers will never write bugs or generate invalid configuration, but it can make sure that one mistake does not affect the entire network. The first major change was to start treating configuration like software. They built an internal system called Snapstone, which packages configuration into deployable versions and rolls them out gradually using the Canary approach. But controlled rollouts only reduce the number of users exposed to a failure. The software still needs to know what to do when the configuration is invalid, and this brings us to the topic of graceful degradation. Cloudflare defined 3 main failure strategies: fail stale, fail open, and fail closed. Fail stale means continuing to use the last known good configuration. If the latest bot model cannot be loaded, the system keeps using the previous one. The detection might be slightly outdated, but customer websites continue working. Fail open allows traffic through without a failed feature. If both the new and previous bot configurations are unavailable, Cloudflare can simply skip bot scoring and continue serving the request. Security is temporarily reduced, but the website remains online. Fail closed, on the other hand, rejects the request because continuing would be unsafe. This makes sense for something like authentication, where allowing everybody through because the permission system is unavailable would be a somewhat questionable reliability strategy. Cloudflare also began separating services into independent traffic cohorts. For example, parts of the worker's runtime are segmented so that changes can reach a small group of free users before moving towards more critical customers. If one segment fails, the other segments can continue working. This is also known as blast radius isolation. At smaller companies, we usually think of a service as either working or broken. At Cloudflare's scale, the more useful question is how many users can be affected by one failure. One request, one customer, or one region might be acceptable, but 20% of the internet is generally less ideal. If you like these blueprint architectural deep dives, you might learn a lot from how Uber is able to handle 40 million database reads every second. Please don't forget to smash all the buttons, and see you in the next one.